Okay, if you're having to watch this from home today because you're absent, we are going through and doing some stuff with converting values from number of charges to amount of charge. And so I started recording a little bit late here, so you missed a little bit. We're going to fill in the remaining portions of this table here in just a minute. All right, 3.74 nanocoulombs. That number, it should be a really large number of protons. And then I'm willing to shout out what they got. We'll see if it matches what I have up here. You feel like you got it, Danny? You feel like you got it? What do you got? That's okay. You did it yesterday? Yeah. You understood it so well that you did it even before I went through this. Let's see. It's times 10 to the 10th, 2.34 times 10 to the 10th. If we need to see it, I'll show it. And again, because I'm recording this, people at home might need to see this anyway. So I'd be happy to show it. Quick show of hands, how many people were able to get the 2.34 times 10 to the 10th? Looks like quite a few, but there's definitely could use some work on this. So let me go ahead and do that one. So I'm going to take that 3.74 nanocoulombs. I would write that 3.74 times 10 to the negative 9 coulombs. That's a positive value, so that means I'm going to have so many extra protons. Again, staying with the conversion factor of using a big number, I'm going to go ahead and do that. 1 coulomb would represent 6.25 times 10 to the 18th. In this case, I'm going to write that as protons instead of electrons, so P plus instead of E minus. And so again, I go through and I make sure that the units reduce out, coulombs and coulombs reduce, and when I'm done, let's see, just from a power of 10 standpoint, that's 10 to the negative 9, the other's 10 to the 18th. If I just add the exponents, that'd be 10 to the 9th. So I'm close, and your calculator will give you the 2.34 times 10 to the 10th, okay? All right. How do I figure out this one? If I don't have just one or the other given, I have both of those given. What would you have to do to determine the net charge? What would you do with that? You subtract. If I have 5 negatives and 3 positives, when you add them together, the net effect would have -2 charge, right? So same idea. We just subtract those. Once you subtract those, determine the amount of charge in coulombs. Give it a go. See if you can do it. Did I do that math right? It's a 7.272. Number of extra electrons. Need to convert that into coulombs. So I agree with Dre. I like using the bigger number instead of the smaller number. It's just easier to deal with large numbers, in my opinion. So I'm going to take that and I'm going to do this as, let's see, I want number of coulombs. So 6.25 times 10 to the 18th electrons in 1 coulomb. So when you go through and do that, I'm just using powers of 10, making sure I haven't made a mistake here. 10 to the 21st, I'm dividing by 10 to the 18th. I subtract those exponents and I get 10 to the 3rd. So my number should be in the neighborhood of 1,000. And what do you get when you actually do that? What do you get there? Yeah, and I'm just rounding that to the closest 10, just because of the significant figures. Okay, and so you get negative 1160 coulombs. Go ahead, Haley.
Are we okay to like convert it to coulombs and then like add them together?
Sure, absolutely.
Okay.
Yeah, that'd be fine too. So what you're saying is convert this into an amount of charge. Convert this into an amount of charge. And then go through and subtract them, absolutely.
Okay.
Yep, thank you. Either one's fine. Okay, we're good? We have to be able to do that kind of math, folks. And the reason for that, just like in your chemistry class, I'm sure you guys had to worry about atoms, number of atoms versus the number of moles and stuff like that, correct? Same idea. You're going to have to do that stuff for electricity. And it should make sense because most of chemistry is done through electric forces, right? So electric charges are able to exert forces on other electric charges through the electric force. I'm going to show you now how to calculate amount of forces based on the amount of force based on charge. We've already studied universal law of gravity. It's developed by Newton. Mass attracts all other mass according to that equation. Well, Coulomb's law is very, very similar to the electric or to the gravitational law. They have the exact same, I'm going to say, parent function. So in your math classes, when you talk about parent functions, you say, this has the same general form. It looks remarkably similar. Instead of G as a constant, we have K as a constant. So there's a Coulomb constant. Instead of M for mass, we have Q for charge. And instead of R squared for distance between their set, we still have R. It's the exact same kind of inverse square law. These are inverse square laws. And since we've seen inverse square laws numerous times now, you should be pretty comfortable with that. You double the distance between two charged objects, what happens to the force? Double the distance, 4 times smaller, right? So increase D or increase R, this force goes down by a factor of 4. Triple the distance, goes down by a factor of 9. So inverse square laws. Charge here serves the same purpose as mass. So if mass attracts other mass, charge can either attract or repel. There are some key differences. G is very tiny. K is very large. And so 8.99 times 10 to the 9th. And the units there, instead of it being Newton meter squared per kilogram squared, it would be Newton meter squared per coulomb squared. So again, instead of kilograms, we have coulombs. They're equivalent kinds of things. Much bigger. Will you turn and tell that person that you're sitting next to how many powers of 10 bigger that is than G? How many powers of 10 bigger? One is 10 to the negative 11, the other is 10 to the 9th. About how far apart are they? 10 to the 20th. So K is about 10 to the 20th times bigger. That's a really big constant compared to G. Now, gravity can only attract. So as far as we know, gravity is just an attractive force. One mass attracts another mass. However, for electric charges, we can either attract or repel. Opposites attract, likes repel. It really depends on whether or not we share the same sign of charge or if they're opposite. So they can either attract or repel, and the K is much, much stronger. Now, for those of you that struggled with the ranking of the electric force versus the other forces, I want to go through and do a quick calculation with you on just how strong the electric force is compared to gravity. The simplest atom, and you guys study this in chemistry class, the simplest one is hydrogen, right? So simple, it has a single proton and a single electron. So we can take this and we can look at how hard, how much force of attraction the electron and proton have because of gravity, and then we can go through and do the exact same thing to say, well, how much force of attraction do they have because of charges? So what I'm going to have you do is I want you to do a calculation here without your calculator. No calculators for this. We're going to do what's called an order of magnitude calc. Order of magnitudes mean just what power of 10. So when I'm done, I'm going to have 10 to some power. Now, I think we agree, we've said this, the electric force is stronger than the gravitational force. It is. If Fe compared to Fg were 10 to the first power, if that's what it was, maybe 10 times stronger. If it were 10 to the second power, how many times stronger would that be? It'd be 100 times stronger. If it were 10 to the sixth power, if it were, how many times stronger would that be? It'd be 1,000,000 times stronger. What I want to do is determine the power, how big that is compared to the other. So I'm going to take a ratio. Now, without a calculator, I want to use powers of 10 here. So let's go ahead and take K. And instead of saying it is equal to 8.99 times 10 to the 9th, I'm going to say it's approximately 10 to some power. What power of 10 would you say K is, knowing that it's 8.99 times 10 to the 9th? You'd say it's 10 to the 10th power. And the reason for that is I'm going to go to the closest power of 10 I can. Well, 8.99 is bigger than 5. So I'm going to round that exponent up to 10 to the 10th. Let's try G. I know it's 6.67 times 10 to the negative 11, but I want to write it as a power of 10. So I'm going to use a squiggly, not an equal. It means it's about this. What power of 10 would you write that as? 10 to the what power? One more time. Negative 10. And again, 6.67 is bigger than 5, so I'm going to take the exponent that was negative 11, I'm going to add 1 to it, makes it negative 10. So we would say K is about 10 to the 10th, G is about 10 to the negative 10th. Okay. Now let's do charges. Q of the electron. Again, folks, you're not expected to memorize these. I would like to know for those that are in chemistry. Probably even AP Chem would probably be the more accurate one for this one. Do you use the charge of a proton or an electron to be 1.6 times 10 to the negative 19? Have you ever seen that number before? Okay, so it's new to us. In chemistry, we're often concerned more about number of charges as opposed to an amount of charge. So how many extra electrons or how many extra protons does something have? So I'm concerned more about a quantity of charge, a number of charge. This is more about the Q value. Okay? 1.6 times 10 to the negative 19, that would be approximately 10 to the negative 19. Now, do you guys notice that the charge of the proton is exactly the same? It's just positive. Okay, so those are just powers of 10. I want to do the same thing with masses. Because charges attract or repel based on the amount of charge they have. Well, masses attract based on the amount of mass they have. So a mass of the electron, approximately what? I know you guys can't see those numbers really well on your table. It says it's 9 times 10 to the negative 31, but from a power of 10, that'd be 10 to the negative 30. Mass of the proton. Well, the proton is about 1,000 times the mass of the electron. So that's where most of the matter is in the atomic nucleus. What power of 10 would that be? Negative 27. Now, the reason I'm doing this with powers of 10 is I don't need to use a calculator for this. All we have to do is just multiply numbers that have the same base. You just add it or subtract exponents depending on whether or not you multiply or divide. I need the size of the size of the atom, of the hydrogen atom. Someone that has their Chromebook up, look this up for me. What is the size of the hydrogen atom? It might give you a radius, it might give you a diameter, I'm not sure, but just look that up for me. Probably going to give you a prefix.
53 pm.
53 pm. That means 53 picometers. Pico is 10 to the negative 12th, I believe. So it's a really small atom, right? I mean, really, really tiny. Do I need to care what the size of that atom is if I'm taking a ratio? I see an R squared in both of those things, which means if I take a ratio, I don't care the size of the atom. Because they're both inverse square laws. Whatever size they are, it cancels for both of them when I take a ratio. So I don't really care what that is. So let's go ahead and now do this ratio. Fe is to Fg as K, Q of the electron times Q of the proton, is to G, mass of the electron times mass of the proton. We're going to do this in powers of 10, so we don't have to use a calculator. K, 10 to the 10th power. The electron, 10 to the negative 19. The electron, 10 to the, or the proton, 10 to the negative 19. Don't need a calculator for that. The denominator, 10 to the negative 10. The electron, 10 to the negative 30. The proton, 10 to the negative 27. The nice thing about this is that when I'm taking multiplications of 10 to some, all you do is add those exponents. What's the numerator turn into? Negative 38 plus 10, negative 28. The denominator? Negative 67. Now, when I do the division, what do I have to do with those exponents? Subtract them. So 10 to the negative 28 minus a negative 67. Check my math here. Am I doing that correctly? Did I do that correctly? 10 to the 39th? Something must be wrong. Because that number is huge. Would you guys agree? 10 to the 39th, big, big, and even bigger number. It's not 10 to the 6 times bigger. It's not a million times bigger. It's not a billion times bigger. It's not a trillion times. It's 10 to the 39 times bigger. Is that a big number? That is a huge number. When I talk about the relative strength of the electric force in comparison to gravity, gravity is so weak we don't even, it's, people can't be responsible for two people falling in love. It is that weak of a force. So the electric force is much stronger, and I can attract or repel. It's pretty versatile, and it's very strong. And hopefully that sort of helps you understand how you would do that math. I want to pull out my Van de Graaff generator for you guys so you can see just how strong that electric force is. I'm going to stop the recording so that we can play a little bit with the Van de Graaff. I'm going to ask you guys to make your way over to that dome.